Hello everyone. So welcome to new lecture of strength of materials, that is principal stresses and strain. And in this chapter, our basic concept, our basic motto is to calculate the stress. What should be the value of stress on an inclined plane? Okay. And if I talk about why it is necessary to calculate the stress on inclined plane, okay, so what happens, in your actual loading conditions, there is both combination of direct and shear stress acting at the same time, okay, and in such conditions the resultant stress across any section, if you want to calculate, will be neither your normal nor tangential to the plane, okay. So in such cases we move to a plane or a oblique plane, you can say, or inclined plane, where our resultant stress will be either normal or tangential. So to solve such type of questions, we need to depth into this chapter. So starting this chapter, let's discuss few terms that will be frequently used in this chapter, okay. So first is principal stress. Oh sorry, let's talk about principal plane first. What is principal plane? So if we talk about principal plane, let's say that this is an material, and material is under your some stresses. Let's say this is sigma 1, this is sigma 1, this is our sigma 2, okay. And during the loading there must be certain if you want to calculate a particular normal a plane, I want to tell at which plane, such that there is only a normal stress. Like if you see this condition at this plane, all of these cases, all of these planes, there is only a normal stress acting, there is no shear stress, okay. So such planes are called your principal planes. So principal planes are those planes on which normal stresses normal stresses acted alone, or I can simply say that or let me write it like this, that is no shear stress, okay. So a plane that has no shear stress or acting on it is or are called principal planes, okay. Now with corresponding to this, we have also a term, that is principal stresses, okay. So if I talk about principal stresses, so principal stress, these are normal stresses acting on a principal plane, okay. Now these your principal stresses generally act in your mutual perpendicular directions, okay, and in both the mutual perpendicular direction your shear stress is 0, okay. So for this principal stresses, there are two type of principal stresses. Like there is a maximum, one is called major principal stress, the second is called minor principal stress, okay. So this major principal stress is generally indicated by sigma 1, and this minor principal stress is indicated by sigma 2. Okay, now this major principal stress is also your maximum value of stress, maximum value of stress. Okay, and this sigma 2 value is minimum value of stress. Okay, so until now we have seen the definition of principal plane and principal stress. Okay, and now if we want to calculate your stress on an oblique plane, so for that it is mentioned like methods of or methods for stress transformation. So what happened, like we have our standard xy axis, we have been like provided with the stress in your standard xy coordinate. Okay, now let's say I have to calculate the stress value at some oblique plane. Okay, so for this we have some another x dash y dash. Okay, so this is called our so we have to like transfer our coordinate. Okay, so this is called your stress transformation. Okay, now this stress transformation is done by two methods. First one is analytical method. The second one is graphical method. Or is also known as like a very famous name, Mohr's circle method. Okay, and this is a very important method. Your most of the questions in your gate and your college examinations are definitely like some questions are from Mohr's circle. So we will discuss in detail. Now there are certain like sign conventions which we should generally follow in your calculation of stress on an oblique plane, and I would like to mention those sign conventions here. Okay, sign. Okay, so first is for your stress. Okay, so for stress we would use positive for tensile or tension, and negative value for compression. Okay, now what happens, like if I okay, so let me draw a diagram first here so that you would like understand this principle. Okay, so let's say that this is your state of stress of an object. Of course there would be some stresses acting. Okay, so let's say that but let me remove this, and first let's only consider that this is your state of stress. Okay, now let's say that you are talking about a plane passing through at an angle theta from the x phase. Okay, theta from the x phase. Okay, on this plane we have to like calculate the value of our stress and strains. Okay, so now we have angle theta, and this angle theta should be from x phase. Okay, now this we are talking about in case of like your stresses, sign convention for, or let's write it sigma stress. Okay, or let me write it for principal stresses. Okay, so we are talking about principal stresses only. Okay, so if we talk about theta, that is we measure from our x phase, so this value of theta would be positive if it is like taken in clockwise direction. Okay, and would be negative if we take it in counterclockwise direction. Okay, so what we have to like look from the x phase, either you are taking it in clockwise direction or anti-clockwise direction. The angle will be your theta. Here we can like from x phase we have drawn theta like this, okay, and okay, so this is also our theta and positive theta this is. Okay, now if I talk about shear stress, so if I talk about shear stress tau, then if I talk about tau, then let me like draw it here. So let's say that the figure will look something like this. Okay, and let's say that tau is acting along this way. Okay, so this will be our counterclockwise loop, this will be our counterclockwise loop. Okay, this is our minus tau. So tau will be like tau can be our positive and tau can be our negative, and it is like in there is another case. Let me draw that case also. Let's say it is acting along this direction. Okay, so what happens, this is our positive tau and it makes an clockwise loop. Okay, so this is how we will calculate, like we will see how the tau acts. So if it is in clockwise direction this will be positive, and it is in our counterclockwise direction it will be negative. And of course this same like conventions are also applicable for your this is our anti-clockwise or counterclockwise, I can say counterclockwise, this is your clockwise. Okay, so if your tau is like in on the x phase, it is like in your okay, so this should be tau is in your like x phase upward direction, it should be negative. Okay, and in downward direction on x phase, so it should be positive. Okay, because it is still in your clockwise direction only. Okay, on y phase we don't like consider this problem. Okay, we have to like we only consider it in one direction, because it always like on both x and y phase the your stress is complementary, we know that. Okay, now moving to next part. So now we will use analytical method to solve our problems. Analytical method, we use this method to find an expression of your normal stress and shear stress. Okay, at any plane which is at angle theta. Okay, now let's say that this is a I would like draw a state of stress for a system. Let's say the sigma x is acting in this direction, sigma x, sigma x, sigma y, and sigma y. Okay, let's say that now we are considering a plane which is at like let's say this plane, we are talking about this plane. Okay, so it is this plane. Let's name this like first let's name it as A, B, C, D. Okay, now let's name the plane as B. Here since I written B, let's call this as E, B. Okay, so on this plane we have to calculate value of our stresses. Sure. Now I have mentioned you that angle from the x phase in clockwise direction is also positive. Okay, here na, in clockwise direction angle is positive. so I have used it. So a theta positive angle is there. Okay, now let's say that the state of stress with the along with your direct stress is also include shear stress. So let's say that shear stress at the x face is this is our shear stress at y face, and both does have the value tau xy. Okay, and similarly here also we will be having some values. Okay, so this is also our tau xy. Okay, this is point A. Okay, now let's say that at this oblique plane there are of course two stresses. One is normal stress. Normal stress is perpendicular to the surface. This is our sigma n, that is normal to the plane considered. Okay, and there is one more stress, that is our tau s, and of course I have like considered it in your clockwise direction only, such that your both tau xy and tau, this is dependent tau s, are considered positive. Okay, so our calculation will be like if we derive a formula, so it will be easier to conclude their things from there. Okay, now so let's see here what will happen if we like cut the plane, cut this element abcd from along this oblique plane. Okay, so let me draw it here. So this is how it looks when like we will explore the figure from this point. So the stress, normal stress and shear stress we have shown is for this part. Okay, so it will act exactly like this in the lower part. Okay, and at this part if we talk about, of course this angle is our this angle from here, like it will be our theta. So this angle is theta. Okay, and our shear stress will be like here tensile, so here also it will be tensile. So normal stress and the shear stress will be in opposite direction. Okay, the shear stress also always exists in a complementary form. Okay, now so if I like consider this part only, if I consider this part, so let me draw a FBD type of this part only. So if we like I go to draw shift this figure, these forces on here. So let me do it first. Okay, so at tau plane, so at theta is so this is our, this angle is our theta, this is our theta. Okay, this is our theta. Okay, so at angle theta we know that along this line, on this line, so in this direction the stress acting is tau s, and in this direction the stress acting is our sigma n. Okay, now of course the rest of the forces we have to mention. So in this direction it is our sigma x, in here it is our sigma y. Okay, and one more thing, along this direction also acting, what is acting? Tau xy. Okay, and along this direction one more force is acting, that is our tau xy. Okay, so these are all the forces that will be acting on this. Okay, but there is a twist, so, like not a twist but a basic concept. So what is the concept that if we want to calculate this value of these value of stresses, we have to like equate the forces in your x and y direction. Let's say this is your x direction, let's say this is your x direction and this is your y direction. Okay, so we have to equate your forces in x and y direction, and these are not stresses, not forces. Okay, so we have to apply, like multiply it by certain factors. Okay, so this tau s is acting on your EB plane or BE plane. Okay, and like if we are assuming 1 unit depth, so area will be B into 1, that is BE. Okay, similarly here also sigma n into BE. Okay, this sigma x will be our BC, and this tau y will be on our EC. EC. Okay, the sigma y will be on our EC, and tau xy will be on BC. Okay, so let's say this axis is x dash, this axis is y dash. Okay, so to apply sigma and tau s, we will apply summation of f forces along x dash should be equal to 0. Okay, from here what we can write, we can write that this sigma n into BE is equal to like component of both of these along this and both of these along this. Okay, so this will be sigma x into BC into cos theta plus tau xy into EC into cos theta plus sigma y into EC sin theta plus tau xy into BC into sin theta. Okay, so from here we can write sigma n is equal to sigma s sigma x times of BC upon BE. So from here we can see that BC upon BE will be based upon hypotenuse, that is cos theta, times of cos square theta. Okay, plus tau xy would become tau xy times of EC upon BE. So EC upon BE is sin theta, and cos theta is there, so sin theta into cos theta plus sigma y into EC upon BE is again sin theta, and sin theta is already there, so sin square theta. Okay, plus now this tau xy and this BC upon BE, as we had discussed earlier, is cos theta, so this will become cos theta into sin theta. Okay, so we can write sigma n is equal to sigma x times of cos square theta. We can write cos square theta is equal to 1 plus cos 2 theta divided by 2 plus sigma y times of sin square theta. Sin square theta we can write it as your 1 minus cos 2 theta by 2. Okay, and plus tau xy times of, so this is sin theta cos theta, 2 sin theta cos theta, this will become 2 sin theta cos theta, so that can be written as sin 2 theta. Okay, so if we expand this, so we can write sigma x is equal to half times of, or let me write it like this, sigma x plus sigma y divided by 2. Okay, plus sigma x minus sigma y divided by 2 times of, from here we will get cos 2 theta. Okay, plus tau xy sin 2 theta. So this is our expression for sigma, not sigma x, sigma n, I'm sorry about this. Okay, this is our expression. Okay, so in here we have like discussed the value of sigma n. Now if I want to calculate the value of tau s, so for that we have to like do summation of f in y dash direction equal to 0. So if I do this, so from here I will get like this, let me write the expression here. So this will be, let's say, sigma y times of EC times of, this is our cos theta. Okay, cos theta plus tau xy into BC times of cos theta is equal to forces acting in this direction. Okay, so this is our tau s into b into b plus then sigma x BC sin theta. Okay, BC sin theta plus tau xy EC sin theta, EC sin theta. Okay, so if I calculate the value of tau s, so I can write tau s is equal to so this is our EC upon BC, EC by BC, sorry, EC by BE. So this is our EC by BE, so this will be sin theta. Okay, tau s is equal to sigma y sin theta cos theta plus now this tau xy times of BC upon BE. So BC upon BE is our cos theta. This becomes cos square theta. Okay, is minus sigma x times of again BC upon BE, that is cos theta. So this will become sin theta cos theta plus minus tau xy EC upon BE is our sin theta. Okay, so this will become sin square theta. Okay, so now if I substitute again, like here I have done 1 plus cos sin square theta as 1 plus cos theta by 2, and cos square theta is 1 minus cos square theta as 1 plus cos theta 2 theta by 2, and sin square theta is 1 minus cos 2 theta by 2. If I substitute it here, so I will obtain tau s is equal to minus half times of, or I can write as minus sigma x minus sigma y divided by 2 times of sin 2 theta. Okay, plus tau xy cos 2 theta. Okay, so this is the expression for our tau s. So we have derived the equation using analytical method for your normal stress and shear stress at a plane which is x degree in clockwise direction from x face. Okay, and since I have mentioned that there are basically two this is a stress transformation. So since we have calculated your sigma n value, sigma n, so this is basically at angle theta, which I have discussed at an angle theta. Okay, now we can also calculate at 90 plus theta. Okay, so now moving to next part, there is a special case. If we talk about, let's say that I want to talk about your complementary stresses. Okay, so complementary planes, there is a term complementary plane, complementary planes. Okay, so what is complementary plane? So mutually perpendicular planes. Complementary planes are mutually perpendicular to each other. Okay, so at theta and 90 plus theta, so these two planes, that is one is theta and another is 90 plus theta, are our complementary planes. Okay, so okay, let me move it on to next page. Okay, so now let's say that I have already calculated the value of sigma n, and that theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 times of cos 2 theta, okay, plus tau xy sin 2 theta. Okay, now let's say I want to write tau s at theta. Okay, so this will become, so if I want to write tau s, so I can like do like okay, so this is like a basic method to remember this formula. This is not any mathematical tool or something. Okay, so we will differentiate sigma and theta, okay, and differentiate in a certain way. Okay, so let's say that this is constant value, so this would be 0, and here sigma x minus sigma y by 2 will remain same. Sigma y by 2 remains same, and then cos, the differentiation of cos is minus sine, and 2 theta will remain same. Okay, so originally what should have happened, your 2 would be like in multiply by 2, but here like I mentioned, this is not like mathematically. Okay, this is just for to remember the formula. Okay, now here again plus tau xy, and sine in differentiation is cos 2. So this is the expression for your tau s theta. Now if I talk about sigma n at 90 plus theta, so what I have to do, I have to do like substitute 90 plus theta wherever our theta is there. Okay, so okay, and so this is also written by your sigma n. Let me write it with another color pen. Sigma n is equal to this, tau s is equal to this, and then again this is sigma n dash complementary. Okay, and similarly we will write tau s dash complementary. Okay, so now we will like, if I substitute theta is equal to 90 minus theta everywhere, so I will obtain it as sigma x plus sigma y by 2 plus, or this would become negative. Okay, minus sigma x minus sigma y divided by 2 times of, so this is cos 2 theta remains cos 2 theta. Okay, now again minus tau xy sin 2 theta. Okay, so and this tau s at 90 plus theta would become plus half times of sigma x minus, or I can write it as like this, sigma x minus sigma y by 2 times of, this will become cos 2 theta, or sorry sin 2 theta minus tau xy cos 2 theta. Okay, now let's name the equations. So let's call this equation to be first. Okay, this is our second equation, this equation is third, and this equation is our fourth equation. Okay, now what we will do, we will first do like add both equations, 1 plus sorry add 1 plus 3. Okay, 1 plus 3 we will add. Okay, so in this case what will happen, so what will happen is, if we add 1 and 3, so this is equation 1 and equation 3, if we add, so we will get sigma n plus sigma n dash equal to, so if we add both these, okay, so this will like cut this will offset this term, so only term left will be this, and if we add both term we will obtain sigma x plus sigma y. So from here what we can say, that sum of stresses x in like two much mutual perpendicular directions is always constant. Okay, even when your angle changes, your plane changes, still your sum of both the stresses in your mutual perpendicular direction remains constant. Okay, now the second thing we will do, we will add the second equation and fourth equation. Okay, and if we do this, so from here we will second and fourth, so this second and fourth, if we do this, we will like see from here this term will cancel out this term will cancel this term, so we will obtain tau s is equal to minus times of tau s dash. Okay, so from using both like this equation and this equation, we can like conclude few points. Okay, so let me write those points here. So the first point I can conclude is that shear stress of two mutual perpendicular planes passing through a point are always equal and unlike in nature. Okay, so shear stress of two mutual perpendicular planes passing through a point are always equal and unlike in nature, like tau s is equal to minus tau dash s. This is also like complementary shear stress they indicate. Okay, if I talk about second point, then sum of they define this statement. Okay, sum of normal stresses on two mutual perpendicular planes passing through a point is always constant and equal to sum of normal stresses in or on x and y faces. Okay, next is, so we can conclude two more like some more points from here. So let's say that so if it is given like this, that sigma x plus sigma y is equal to 0, what would this mean? This mean that complementary normal stresses are equal and unlike in nature. So we can say from here that sigma n theta is equal to minus times of sigma n at 90 plus theta. Okay, and tau s at theta is equal to minus tau s, this is always true. Okay, 90 plus theta. Now like we can also write this term equal to sum of principal stresses sigma 1 plus sigma 2, because sigma 1 and sigma 2 are also in mutually perpendicular planes. Okay, now we will consider a special case, and that special case is when your special case is principal plane case. So what happen on principal plane? On principal plane, your tau s equal to 0. Okay, and sigma n is maximum. Okay, so how can we like do this? So let's calculate the location of your principal plane and what should be the value of your principal stresses. So we already know the value, like the state expression for your tau s is equal to minus of sigma x minus sigma y by 2 times of sin square theta sin 2 theta plus tau xy times of cos 2 theta. Okay, so from here what we can write, we can substitute this equal to 0. Okay, so let's say that theta principal plane angle is theta p. Okay, so from here what we can write, we can write tan 2 theta p principal is equal to, what will become our 2 tau xy upon sigma x minus sigma y. This is the expression for principal plane angle. Okay, and this theta is, as we'll know, from our x face in clockwise direction. Okay, now if I want to calculate, let's say, your principal value, stress value, so we will use this expression sigma n is equal to sigma x plus sigma y divided by 2 times of sigma x minus sigma y divided by 2, okay, times of cos 2 theta plus tau xy times of sin 2 theta. Okay, so what we can do from here, so if I want to, let's say, calculate sigma 1 or 2, if I want to calculate, let's say, sigma 1. Okay, so let's substitute the value of theta p. We write the value of theta p is here. We will get the equation as sigma 1, 1 and 2 both will be given by sigma x plus sigma y divided by 2, okay, plus minus times of square root of your sigma x minus sigma y divided by 2 square plus tau xy square. Okay, so this is our relationship for principal stresses. Okay, and this is for your principal plane angle. We can look into your tau max plane. Okay, so the principal plane was where our shear stress is 0 and your normal stress is maximum, and similarly there will exist a tau max plane, and at tau max plane your tau is of course maximum and sigma will exist, may or may not be 0. Okay, so to find the location of tau max plane, what we have to do, we have to differentiate the tau s equation and put it equal to 0. Okay, and if we do this, so we will obtain tan 2 theta is equal to, and theta of max plane is equal to minus sigma x minus sigma y divided by 2 tau xy. Okay, so we can write that tan 2 theta as shear plane, okay, will be equal to minus 1 upon 2 tau xy upon sigma x minus sigma y. This is our tan 2 theta s. Okay, and if we look into this formula, so this is our tan theta p 2p, so we can write it is equal to minus 1 upon tan 2 theta p. Okay, and from this equation what we can write, that tan of 2 theta s into tan of 2 theta p is equal to minus 1. And what does this mean? This means that our shear plane and our principal planes are perpendicular to each other. Okay, not exactly perpendicular, I mean like here 2 theta s and 2 theta p are 90 degree apart. Okay, so we can say that theta s and theta p are 45 degrees apart. Okay, so if I know the one of the values, so if I say that theta 1, if I say, let's say that theta 1 and theta 2, these are our principal plane angles, and if I talk about, let's say, shear plane angles, so if I take about let's say the theta 3 and theta 4 are our shear plane angles. Okay, so if I want to calculate principal plane, so this will be our theta p. Okay, and 90 plus theta p. Okay, and theta 3 if you want to calculate, so theta 3 will be equal to our theta s, or can be also written as theta 1 plus 45 degree. Okay, and similarly theta s can be written as our, so theta 4 can be written as theta s plus 90. Okay, and can be also written as theta 2 plus 45 is equal to theta 1 plus 45 is equal to 45 plus, or let me write it, theta p, principal plane angle, plus 45 degree. Okay, and here this will be equal to theta p plus 135 degree. Okay, so like there is a difference of 45 degree between your theta p and theta I mean a difference 45 between 45 degree between your principal plane and shear plane angles. Okay, and of course your two consecutive principal angles are 90 degree apart, and shear plane angles are 90 degree apart. Now let's say that it asks about the shear stress value. What should be the shear stress at your shear maximum tau max plane? So as I mentioned here, that tau star is the shear stress on normal stress on your shear stress plane. Okay, so we can calculate tau star sigma star using your sigma and theta equation. Okay, and using this equation we can calculate the value of your normal stress on tau max plane. Okay, so now we will be moving to our new topic, and this topic is, if I like, we have discussed 3 cases up till now. So first case was your principal plane case, second was tau max plane. Okay, and third, if we talk about, then third one is your pure shear. So in case of pure shear, as we can say that sigma will be equal to 0 and tau will exist. Okay, so since we have to calculate such plane, so what we will do, we will equate sigma n at theta equal to 0. Okay, and from here we will obtain our theta 5 and theta 6. Okay, so theta 5 and theta 6, but here we can remember one thing, that the theta 5 and theta 6 are our non-complementary. No, complementary. Okay, non-complementary. So it isn't like theta 6 will be 90 plus theta 5. This won't be like this condition won't be happening here. Okay, Now now if I want to like talk about shear stress on this pure shear plane, so this would be like less than equal to tau max. Okay, this is only possibility. Okay, and there are some conditions which I would like to discuss in after your Mohr circle discussion. Okay, so I will discuss it there. So now we will start our next approach, that is graphical approach. So up to here, like, we have completed our analytical approach. Now we will move to graphical approach or graphical method. Okay, and this is our Mohr circle method. Okay, so now, so we know that after stress transformation, our equations are given by sigma x dash, okay, is equal to sigma x, or basically this is our sigma n theta, okay, is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau x y sin 2 theta. Okay, and tau s theta can be written as tau x dash y dash, and this would be equal to minus of sigma x minus sigma y divided by 2 times of sin 2 theta plus tau x y times of cos of 2 theta. Okay, so like if I do few things in your first equation, so from here I can write the sigma x dash minus sigma x plus sigma y divided by 2. Okay, this term would be equal to your sigma x minus sigma y divided by 2 times of cos 2 theta plus tau xy times of sin 2 theta. Okay, and if we square both side, so we will obtain like this term will remain, let's keep this term same, and if we expand this term, so we will obtain sigma x minus sigma y by 2 square cos square 2 theta plus tau xy square sin square 2 theta plus 2 times of tau xy into sigma x minus sigma y divided by 2, or if I remove 2 from here, so I can write it as sin 4 theta. Okay, so now if I like do the square of this tau x dash y dash, so tau x dash y dash square can be written as your sigma x minus sigma y by 2 square sin square theta plus tau xy square cos square 2 theta, here it will be 2 theta, okay, minus tau xy sigma x minus sigma y divided by 2 times of sin 4 theta. Now let's say I add both these equations. So if I add both these equations, so I will obtain, if I add both these equations, so let's see here, sigma x dash minus sigma s minus sigma y by 2 square, okay, and square of this plus tau x dash y dash square of this term, and this will be equal to, like, if I add both these and this, so we know that sin square theta plus cos square theta is equal to 1. So this term will become sigma x minus sigma y by 2 square plus similarly tau x y square, and this term will cancel out each other. Okay, so this term we will obtain this equation. Okay, now if I compare it with your standard equation of circle, so what is we write in standard equation of circle? I write it as equal to x minus a square plus y square is equal to r square. If I compare it to this equation, so I will obtain few terms, and these terms will be your a, that is your center. Okay, so the center will be at your sigma x minus sigma y by 2, and this is our center in center. Okay, so I will show this to you later. Okay, center, this is the only x coordinate of the center. Okay, let me write this equation in standard form. Y minus b square is equal to r square. So this is our standard equation. So from here we can write the center of Mohr circle will be at your a comma b. So this will be sigma x minus sigma y by 2 a, and b is 0. Okay, so center lies on your x plane. Okay, now if I talk about your radius. Okay, so radius r is equal to square root of sigma x minus sigma y by 2 square plus tau xy square. Okay, so this is our center, and this is our radius of your Mohr circle. So this term here is plus actually. Okay, so this should be plus. Center is sigma x plus sigma y by 2. I hope I have written correct here. Okay, yes, this is correct. Now let's talk about the definition of Mohr circle. So if I talk about the definition, so Mohr circle is basically locus of points which represent normal and shear stresses on various planes passing through a point on a body. So on a given point there are infinite number of planes passing through this point. Okay, and the locus of the stress value on all the planes at that point is our Mohr circle. Okay, so there are basically, let me draw a Mohr circle to show you the example. So there are basically two axes. One is y axis. Okay, as I from this equation we can say our y axis is tau xy. Okay, so this is our tau axis. Okay, now there is an x axis. Okay, and the x axis is our sigma axis. Okay, now let me move it in center. Okay, now your Mohr circle is basically a circle as I have defined. This is a circle. Okay, and this circle have its center, is a circle with its center lying on this x-axis x-axis and does have like the value of as sigma x plus sigma y by 2. Okay, x coordinated, y as this, and but y coordinate is our sigma x sigma by 2. Okay, so this circle can be anywhere on this, like it can be here, it can be here, it can be perfectly like fitted between these two. Okay, or it can be some random point, let's say this point. Okay, so let's keep it here now. For now, let's keep it here. Okay, now these points, the nomenclature for all these points, let me name those, show those points here. Okay, so this point is our sigma 1, is our major principal axis sigma 1, and this point is our sigma 2. Okay, let's say that this is our center, and this center is represented by C. Okay, and the radius of the Mohr circle is this is our radius of Mohr circle represented by R. Okay, and of course sigma 2 is this length from O to here. Okay, now let's name this A, this is our B. Okay, now at any point, if we like extend a line from origin O at any point P, so this will show you your resultant stress. This will show you your sigma sigma resultant stress. Okay, and it generally at an angle beta from your major principal stress. Okay, this is our at an angle beta. Okay, and this maximum point, it attains the maximum point here. The maximum point is our tau max. This is our tau max. Okay, now so this length from here till center, this length is basically our sigma x plus sigma y by 2, or we can also write it as sigma 1 plus sigma 2 by 2. I hope you understood till here. Okay, and this R value, this R is equal to our tau max, we can see from here. Okay, R is equal to tau max, and of course it is equal to your like if I want to calculate this radius, so I can write it as sigma 1 minus sigma 2 divided by 2. Okay, and of course we have an expression of R as sigma x minus sigma y by 2 square plus tau xy square total under root. Okay, what else we can mention? And of course this your center lies on your plane of, like the stress on the center, the value of stress, that is our sigma star, lies on your plane of maximum shear. Sigma star, this is basically sigma star, and the stress which lies on your maximum shear plane. So OA is our sigma 1 major principal stress, and OB is our sigma 2, that is minor principal stress. Okay, and the angle beta is your angle of obliquity, obliquity. Okay, how much like the angle between your resultant stress and major principal stress. Okay, this is our beta. Now from here we can say what generally happens, like we talk about your angles, angle in your analytical way. So we know that major principal planes, and in the Mohr circle, like Mohr circle subset 2 theta angle. So we see that between the principal planes angle there is angle of 180 degree. But in actual what is the angle? In actuality the angle is 90 degree, but here it is 180 degree. So we can say that 2 points on circumference of Mohr circle subtends an angle 2 theta at center. Then angle between those two planes are theta. Okay, actual angle is theta, but it will be showing the angle 2 theta on your plane. Okay, now there is a special case. A special case is when like your sigma x plus sigma y by 2 is equal to 0. If your this term is equal to 0, it means that your case of pure shear, it means that center lies on your 0, 0. Okay, and this is the case of your pure shear. Okay, and like the Mohr circle will look like this. This is sigma and tau axis, and it will be like centered at origin, and this is our R. Okay, so this tau is equal to sigma 1 is equal to sigma 2 magnitude wise. Okay, and sigma 1 and sigma 2 will be our unlike. Sure, we can write it as equal to this point is tau. Our sigma 1 is tau, sigma 2 is minus tau. Okay, and tau shear stress is tau. Okay, so I hope you understand it. So we know that sigma 1 is equal to tau, sigma 2 is equal to tau, minus tau. It means that your sigma 1 plus sigma 2 is equal to 0. Hence your sigma x plus sigma y is equal to must be 0, and hence this condition is satisfied for this condition is for pure shear. Okay, now we will see for hydrostatic pressure. In case of hydrostatic pressure, what happens? In case of your hydrostatic pressure, we know that your sigma x will be equal to sigma y, and b will be equal to minus p. Okay, it is something like this, na? So on the below your is under like your pressure, hydrostatic pressure. So pressure P will be acting from all directions. Okay, and this is negative. Okay, in compression, so negative P. So sigma x is equal to sigma y is equal to minus P, and hence if you want to show it on your Mohr circle, it is shown by like this is our tau axis, this is our stress axis. Okay, so we can show that this point here represent our minus P, this point here represent minus P. Okay, and why it is point, this is our center. And if we talk about the radius, so we know that radius is given by sigma 1 minus sigma 2 by 2. This is our radius. Okay, and this is also equal to our sigma 1 and sigma 2. Okay, so we can say that radius is equal to 0. So your Mohr circle for hydrostatic pressure, under hydrostatic pressure, is the point on the negative axis of your stress. Okay, so from here we can say that your hydrostatically constrained object, or under the hydrostatic loading, your object does not have any shear stress acting on it. Okay, so let's say that if it is asked about a material, like if you are given the material and you have to apply such load such a type that there won't be any shear stress at any plane acting on it. Okay, so what we will say that if we apply the hydrostatic load on that material, there won't be any shear force acting at any plane. Okay, I hope you understand till here. Now let's say for a given loading condition, if we want to draw a Mohr circle, so let's consider a loading condition. Okay, so let's say that this is sigma x, okay, and this is sigma y, sigma x, and this is our sigma y. Okay, let's say this is our shear stress tau xy, and similarly this is also our shear stress tau xy. Okay, so let's say I want to draw your Mohr circle for this element. Okay, so first let me draw the axis first. So let's say this is your tau axis, this is your sigma axis. Okay, so we will see that there is a point. Let's say this is our, if we talk about x phase, so at x phase our tensile stress of sigma x and shear stress of tau xy, and that is in positive direction. Okay, so sigma x, let's say this is our, this here point represent our sigma x, and let's say this is our tau xy. Okay, this is our sigma x comma tau xy. Okay, and if we talk about sigma y, so let's say this is sigma y, and here it is our tau xy again. So this is our sigma x minus comma minus tau xy, because y minus, because on the y plane it is acting in clockwise direction tau xy, so it will be negative. Okay, now we have to draw a circle such that it passes through both of these points. Okay, and having the center at this. So let me define it again. Okay, so this is our so this is our Mohr circle, and it does passes through your both of these points, this point and this point, and have the center, of course center. Okay, so I forgot to mention first center. So your if you want to draw, so center, you will mark the center point, that is your sigma x plus sigma y by 2. Okay, comma 0. So this is your center point. You mark center point, and you'll put a compass from here to here and draw a circle. This is your Mohr circle. Okay, now if you want to calculate all the values, so we can calculate here. So this point here will be our sigma 1, of course. This will be indicating our sigma 2. Okay, so here what I have shown you how to draw your Mohr circle, and of course this is your diameter of Mohr circle. Okay, now so from this figure we can see that this from this plane, this indicate this plane x face. Okay, so from x face, this is at angle 2 theta p is our principal plane. Okay, and another angle is from here to here, that is your 180 plus 2 theta p, 180 plus 2 theta p. Okay, so we can also write it as twice of 90 plus theta p. Okay, so we can say that theta p and both the principal angles are 90 degree apart. Okay, principal planes are 90 degree apart. So let me remove these points from here. Now we will see how to solve, do the calculation. So let's consider this as our Mohr circle, as we have considered in previously. Okay, now so let's say if we have drawn a Mohr circle for a given problem, let's say that these. Okay, So let's say this is the Mohr circle you have obtained, okay, by like this. These are 2 points, two faces, our x face and y face, and by using this you have obtained this Mohr circle, okay. So let's say we have to calculate the various terms. So how will we calculate them? Of course, in graphical way we can like measure all the angles, like all the point values, and we can calculate uh, all the values, okay. But in examination what we have to do, so we will like look in with respect to that point only, okay. So we have to calculate major principal stress, minor principal stress, tau maximum, okay, and your plane of zero shear stress. On zero shear stress there will be some stress, normal stress on plane of pure shear, not pure shear, on zero shear, okay. Then shear stress on plane of pure shear. We have to like calculate these values, okay, of course. And theta, principal planes angle, okay, shear plane angles, okay, shear plane angles. So we will see how to calculate all of these angles, okay. So we know that this point is given as sigma x comma tau xy, okay, and we know that the center value is our sigma x plus sigma y by 2, okay. So to calculate the value of your sigma 1, that it will be equal to OB. So what we can do, we can write it as OC plus CB, okay, and our OC is sigma x plus sigma y by 2, okay, plus radius of Mohr circle, and we know that radius is calculated using your square root of sigma x minus sigma y by 2 square plus tau x square, okay. So using this relation we can calculate the radius of Mohr circle, and from here we can calculate our sigma 1. If I want to calculate sigma 2, this is our OA, okay, and this is our AC minus OC is equal to radius minus sigma x plus sigma y by 2, okay. So we have calculated our sigma 1 and sigma 2 values, okay. Now let's say this is our P, and let's say this point is our Q, okay. This point is let's say our X, okay. So to calculate your theta P, okay, so let's first calculate our tau max. So tau max, we know that this is equal to radius is equal to R, okay. Sigma n star is the like shear stress value at zero shear plane, sorry, tau max plane, okay. So this value will be equal to our sigma x plus sigma y by 2. So this point here is our sigma star comma tau max, okay. Sigma star is normal stress at tau max plane. Now tau s star is shear stress at pure shear plane. So this will be at this point, like our shear stress is shear stress, and here our normal stress is 0, okay. So we will write 0 comma tau s star, okay. This is our plane of pure shear, okay, plane of pure shear. So like if I do some mathematics, so this is the plane here, okay, this plane, and this angle will be our 2 beta, that is the plane of your pure shear plane, okay. But before that, let's calculate like theta p and theta s, okay. So this angle is our 2 theta p, okay, and this angle is our 2 theta s, okay. So if I want to, let's calculate theta p. So I can write for calculation theta p, what I can write? I can write that tan 2 theta p is equal to px upon cx. Okay, and value of px is your tau xy, and value of cx, if I talk about cx, so this will be your sigma x minus center c. Okay, that is sigma. So again, of course, we will obtain the same relation we had obtained previously, 2 tau xy upon sigma x minus sigma y. Okay, now let's say I want to calculate theta s. Okay, so theta s we can directly calculate using from this relation what we can write, that 2 theta s is equal to 90 minus 2 theta p. So from here we can directly calculate our theta s values. Okay, now let's say now I want to calculate out tau s star. Tau s star I want to calculate. Okay, so from this figure what we can, let's rename this, name this, so pq, let's call this point s. Okay, so what we can write from here, and one thing I forgot to mention, this is our sigma 1 minus sigma 2 by 2. Okay, these are equal to this. So if I want to calculate tau s star, so let's see in the triangle OCS. So from here we can like that CS square is equal to OC square plus OS square. Okay, now CS square is our sigma 1 minus sigma 2 by 2, that is our R square. Okay, is equal to OC square. OC square is our sigma x plus sigma y, or I can also write it as sigma 1 plus sigma 2 by 2 square plus OS is our tau star square. Okay, so from here we will get our tau star is equal to, so if we expand and solve this, so we will obtain value is equal to minus of sigma 1 sigma 2. Okay, and why this minus term? Because one of the sigma 1 and sigma 2 will always be negative in case there is a presence of your pure shear plane. Okay, now if I want to calculate, let's say the the angle, this is the inclination of the pure shear plane, so we can write, so let me, instead of here, let me write it here. So we can write tan of, now here this is 2 beta, so this will be our 180 minus 2 beta. 180 minus 2 beta is equal to tau star divided by sigma 1 plus sigma 2 divided by 2. Okay, now what we can write, so we know that our this sigma star is root of minus sigma 1 sigma 2. Okay, and this is our sigma 1 plus sigma 2 by 2. So if we solve this, so we obtain our tan beta is equal to root of minus sigma 1 by sigma 2. Okay, so I hope you understood till here. Now there are we have described few terms previously, so let me mention those here first. So if I mention that in plane tau max, so in plane tau max is our basically it will indicated by tau max is equal to your tau max from your Mohr circle, which is generally given by your radius. Okay, or is also written as sigma 1 minus sigma 2 by 2. Okay, This is your in plane tau max. The next is our absolute tau max. So absolute tau max is basically like maximum of sigma 1 minus sigma 2 by 2 comma sigma 2 minus sigma 3 by 2 comma sigma 1 minus sigma 3 by 2. So absolute of like all three, so maximum of all three is our tau max absolute. Okay, and sigma 1, sigma 2 and sigma 3 are major principal axis, minor principal axis and intermediate principal axis respectively. Okay, up until this point we have like discussed our stress analysis. Now we will talk about our strain analysis. Strain analysis. Okay, so we know that our strain like E1 is given by sigma 1 by E minus mu times of sigma 2 by E, and epsilon 2 is given by sigma 2 by E minus mu times of sigma 1 by E. This is in case of your 2D state of stress. Okay, now if I like want to calculate sigma 1 and sigma, let's say that I know the value of our strains and I want to calculate stress, so I will calculate by like if we rearrange the above two formulas, so I will obtain E minus 1 by E upon 1 minus mu square times of epsilon 1 plus mu times of epsilon 2, epsilon 1 plus mu times epsilon 2, and here also E times of E upon 1 minus mu square times of epsilon 2 plus mu times of epsilon 1. Okay, so this is our relation between stress and strain. If like our strain values are known and we want to calculate the stress value, so we can use this equation. Now again, for strain analysis of a given system, we have two methods, that are our analytical method and graphical method. We will see both methods here, but there is slight difference, like difference in our sign convention we use. So sign convention, here our sign convention will be like, if we talk about strain, so strain will be positive and negative. This is standard case. Okay, and what else, like our value of theta. If I talk about theta, so theta here is measured in case of stress it was measured from your x phase. Okay, but in this case like theta is measured from your x axis. Okay, so let's say that if I want to calculate at any point, so theta will be measured from here. Okay, so this is our theta, and this is if it is positive, if it is anti-clockwise or counterclockwise, and negative it is clockwise. Okay, now like if we derive the formula, so we will get like what we obtained in our case of stress, but slight difference, because let's say that first state of stress, let me write a stress of stress in our form of your strain. So it is our epsilon x epsilon y gamma xy by 2 and gamma xy by, so this is our shear strain. Okay, I hope you understand this point. Okay, now how strain is measured, let's first talk about how strain is measured. So it is measured with the help of strain rosettes. Okay, so we obtain like install it along the directions we want to measure our strain, and along those directions it will give us certain values, and we will obtain our value of epsilon x epsilon y or whatever we want. Okay, now if I derive the formula, so similar to our how we obtained for our stress condition, here we will obtain that epsilon x dash is equal to epsilon x plus epsilon y by, or let's call it like, okay, so this was good. Okay, epsilon x dash is okay, by 2, or let's call it like epsilon normal theta at theta angle. Okay, plus epsilon x minus epsilon y by 2 times of cos 2 theta plus instead of tau xy we use here phi xy by 2, okay, times of sin 2 theta. So this is our equation for normal uh, strain, okay, longitudinal strain. And if I talk about shear strain, so we write it as phi, or like, since I have used gamma, I have mentioned gamma here now, okay, so let write gamma here, okay, gamma times of, okay, so we write it as gamma s by 2 at any theta angle, will be given as minus times of epsilon x minus epsilon y divided by 2 times of sin 2 theta plus gamma xy by 2 times of cos 2 theta. So this is our relationship, okay. So here also, like, we can calculate our principal strain plane, that is tan 2 theta p is equal to, there it was 2 tau xy upon sigma x minus sigma y. If I replace, so like what we do, we replace your let me write it here. So in this condition, what we do, sigma x we replace by epsilon x, sigma y we replace by epsilon y, okay, and tau xy we replace to gamma xy by 2, okay. So here we obtain tau tan 2 theta p is equal to gamma xy divided by epsilon x minus epsilon y. This is our principal plane angles, okay, and the values can be obtained as epsilon 1 comma 2 is equal to epsilon x plus epsilon y by 2, principal strain values we are talking about, okay, plus minus square root of epsilon x minus epsilon y divided by 2 square plus gamma xy by 2 square, okay. So this is the relation. So here also, like similar to our stress analysis, we can write certain statements, like we can write that epsilon n at theta plus epsilon at and at 90 plus theta, same application, same rules are, same theories are applies here also, okay, is equal to epsilon x plus epsilon y will be equal to epsilon 1 plus epsilon 2, okay. We can write that shear strain at theta is equal to minus times of shear stress at 90 plus theta, okay, and we can say that radius of Mohr circle will be given by epsilon 1 minus epsilon 2 by 2, okay, and center can be given by epsilon 1 plus epsilon 2 by 2 comma 0, okay. And similarly we can also talk about like absolute or in plane your gamma max by 2. Let's talk about this, okay. So we can see this is equal to absolute if we talk about gamma max by 2, absolute if we talk about, so we will see this as maximum of epsilon 1 minus epsilon 2 by 2, okay, comma epsilon 1 minus epsilon 3 by 2, comma epsilon 2 minus epsilon 3 by 2. So maximum of these three values will be our gamma max by 2, that is absolute. If we talk about in plane, so this is our like we can calculate it using your Mohr circle, okay. So Mohr circle will be like drawn like this. Let me draw it here only. So this axis will represent, we like I can write it is 5 by 2, or I can also show by gamma by 2 using gamma by 2, okay. And here the x-axis will be like representation of our strain, Okay, and rest everything is will remain same. Okay, now the next topic if we talk about, we will talk about strain rosettes, various formations of your strain rosettes. Okay, so like strain rosettes are defined as the arrangement of three strain gauges along like different directions. Okay, so there are three types of strain rosettes. First is rectangular, second is delta, third is star. In rectangular, what happens? In rectangular, alpha is equal to 45 degree and theta is equal to 0 degree, 45 degree and 90 degree. These three angles is applied. Alpha is equal to like angle between each one of these. Okay, and theta is equal to 0 degree, 60 degree and 120 degree. In star, alpha is equal to 120 degree, that is between two strain rosettes, and theta are 0 degree, 120 degree, 240 degree. Okay, so this alpha is the angle between strain gauges. Okay, and theta is the like inclination of strain gauges. Okay, so we will look like how the diagrams look for each of three cases. Okay, so let's see. First case I talk about, that is rectangular. Okay, so it is given something like this. So there are three axes, x axis, y axis, x, y, and there is another one in the middle, that is at your 45 degree. This represent alpha is equal to 45 degree. Okay, now there are three strain rosettes strain gauges applied positioned here. So let's say this is the strain gauge A, this is our strain gauge B, and this is here we have used our strain gauge C. Okay, so this line indicates our theta is equal to 0, theta is equal to 45 degree, and theta is equal to 90 degree. So what we can write from here, that strain in strain gauge A will be our strain in x direction. Okay, and normal strain at theta equal to 0. Okay, and strain in C is equal to strain in y direction, that is our normal strain at theta is equal to 90 degree. Okay, and strain in B is equal to normal strain at theta is equal to 45 degree. Okay, so we will use these strain values in your equations using this formula. As theta is equal to 45 degree, from here we can write like that strain in B is equal to, and this is like if we put theta is equal to 45, so we will obtain half times of or we like write it as epsilon A plus epsilon B by 2, and if we substitute theta is equal to 45, so cos 90 value is equal to 0, so this value will become 0 plus gamma xy by 2 times of 1, this value will become 1. Okay, so from here we can calculate that gamma xy is equal to 2 epsilon B minus epsilon A minus epsilon C. So using this relation, we can calculate the gamma xy. So we have all the values of epsilon A, epsilon y and gamma xy, and using this equation and this equation further, we can calculate our required strain at any point. Okay, so our main purpose of using 3D strain rosettes are to calculate our strains in like two perpendicular directions and one shear strain. Okay, now we talk about second arrangement, that is our star arrangement, which we have so delta arrangement I have mentioned earlier. So second arrangement is delta star rosette, delta. Okay, so in delta it is of course in form of your equilateral triangle. Okay, this is our like reference plane. Okay, and of course 3 strain rosettes are applied here too. So let's say this is our rosette A or gauge A. Okay, so this is our gauge B, and this here is our gauge C. Okay, so this is our alpha is equal to 60 degree. Okay, this is theta is equal to 0 degree. This is our theta is equal to 60 degree and theta is equal to 120 degree. Okay, this is our 120 degree. Okay, so we can write that epsilon A is equal to epsilon will be epsilon x in the x direction. Okay, and epsilon b will be at epsilon n at theta is equal to 60 degree. Okay, epsilon c will be epsilon n at theta is equal to 120 degree, and using this both we can calculate epsilon. We know epsilon x, so we can calculate epsilon y, and we can also calculate gamma xy. Okay, so this is our purpose will be completed here. Now third type of arrangement is our star arrangement, which we have mentioned, which I mentioned earlier. So it is something like this. Okay, so our 120 degree is our alpha. Okay, and strain rosettes are applied 3. This is, let's say, A, this is our B, and along this is our C. Okay, so this is our let's say theta is equal to 0 degree, theta is equal to 120 degree, and theta is equal to 240 degree. Okay, so we can write that epsilon A will be equal to your epsilon x. Okay, and epsilon B will be equal to epsilon n at theta is equal to 120 degree, and epsilon C will be epsilon n at theta is equal to 240 degree. Now from using this equation we can calculate the value of epsilon y and gamma xy. Okay, and we can like process with our actual question, whatever it was. Okay, whatever it is asked. So this is our concept behind your strain rosettes. So using this strain rosettes we can like we have obtained value of epsilon x, epsilon y, and gamma xy. Now using these values we will obtain epsilon 1 and epsilon y, and using this epsilon 1 and epsilon 2, and using this we will obtain our sigma 1 and sigma 2 values. Okay, we know that it is given by 1 minus 1 upon 1 minus mu square is equal to epsilon 1 plus mu times of epsilon 2, and it is 1 upon e upon 1 minus mu square times of epsilon 2 plus mu times of epsilon 1. Okay, so to calculate so what is the purpose of using strain rosettes? It is to calculate our value of stress. Our main purpose is to calculate the principal stress values. Okay, I hope you understood till. So with this we will be concluding our chapter, that is principal stress and principal strains. Okay, thank you.